Welcome to Physical Chemistry Chats. The pain doesn't stop, it just keeps on going. This is part 3 of chapter 9, where we're looking at ideal and real solutions. In this episode, we'll look at the real solutions and how they differ. So go ahead and get right into it for now. Let's see, let's go ahead and go with the screen in general. Okay. Come on. There we go. And now. There we go. Oh, crap. Too far. So, basic idea, up until now, we've been dealing with real ideal solutions where each compound is assumed to react identically. That if I mix a solute and a solvent, and they're both liquids, they'll have similar intermolecular forces, so that solute-solute interactions are of equal strength to solvent-solvent interactions, which are equal strength to solute-solvent interactions. So I mix toluene with benzene. The benzene treats the toluene like the toluene treats the toluene. The benzene treats the toluene like the benzene treats the benzene. So they all kind of mix equally, and there's no one molecule that treats the other like something else. But that's rarely, if ever, the actual case. I mean, even with things that are perfectly miscible, like ethanol and water, ethanol does not perfectly mix with all the water. In fact, the majority of the ethanol molecules are migrate to either the top or the bottom of a solution. So such that like the aromatics that are soluble in alcohols, and like say your vodkas and your whiskeys or whatnot, you mean mostly on the top, so you're going to get the most smell up. And when you add that water, add that little drop of water to your whiskey, it's going to then release all those aromatics into the vapor phase, which is what changes the aroma and the character of your whiskey. And now that's because it's a real solution and not perfectly mixed throughout. It's not 100% mixed. Now, depending on whether your solvent interactions are greater than or less than the pure solute or the pure solvent forces, we'll get some negative or positive deviations from what is expected. Just looking at Raoult's law, we're mainly looking in terms of Raoult's law, that you say the partial pressure of a gas is equal to the pure pressure of that gas times its mole fraction. An ideal solution, this is a linear relationship. It's not always the case. So we'll also notice that delta G of mixing is going to be spontaneous. Entropy of mixing is always going to be spontaneous. But here's what's really new, that the volume of mixing should not be zero. And entropy of mixing should not be zero. This is our big change. That these guys could be positive or negative depending on the strength of these interactions. In a real solution, the delta and the volume of mixing is not just going to be the volume of A times its mole fraction plus the volume of B times its mole fraction. So like, it's not going to just be the sum of the volumes of those guys. It's going to be basically, how do they pack together? You should know this. So like, if I take a giant basketballs and I throw in some ping pong balls, you're not going to get the sum of the volume of basketballs plus the volume of ping pong balls, because the basketballs will have a bunch of gaps in between them because they're round and they're spheres and they won't fit. The ping pong balls can pack in between those. And so you're going to see a negative volume of mixing. You're going to see the less volume than you would expect So sometimes you're going to see a larger volume mixing because they're going to repel each other and they're not going to pack nicely. And of course, depending on the interaction, so you have to break up the solute and the solvent. You're going to break these intermolecular forces and make new intermolecular forces. And if the starting ones are stronger than the ending ones, you're going to see endothermic. If the ending ones are stronger than the starting forces, you're going to see exothermic mixing. So let's first by looking at partial molar volume. As I said, that enthalpy, the volume of mixing is no longer zero because with unique intermolecular interactions will change the molecular packing depending on the local environment. So water should have a molar volume of 18.1 centimeters cubed at room temperature. If you mix 1 mole of ethanol in water, so that the 1 mole of, mix 1 mole into a large ethanol water solution where the mole fraction of water is 0.75. Such quantities, the addition of 1 mole of water is negligibly changes the mole fraction. So you say, I have like say 1,000 moles of water ethanol mixture where it's 75% water. If I add just a little bit of water, the change for that molar volume is not 18, which is what you would expect for 1 mole of water, but 16. So it is not taking up nearly as much space as you would expect because of how the water ethanol mixtures interact. This is an example of what's called partial molar volume. The volume that changes as the component I is sufficient quantities of the solution. Essentially, that right there where it's like, it's in large enough quantities that 1 mole does not affect the overall mole fraction by much, but how does the fact that mole fraction interact that addition of a small microscopic quantity? So the volume of solution then becomes the moles of A times the partial molar volume of A. The moles of B, partial molar volume of B, where these guys are interrelated, much like the same thing with chemical potentials. So we can look at it, like if we divide both sides by volume, divide both sides by the total moles, get the mole fraction A, mole fraction B, and look at how these change. So as 1 molar volume goes up, the other must go down. Vice versa. So here's a mole fraction of chloroform in, I'm not sure what type of solution that is, but as the mole fraction goes up, you see how does the partial molar volume change? When chloroform solution is low amounts of chloroform, we're seeing much greater than, well, you see like slightly greater than what you would expect. And as we get down to 0.6 mole fraction, we see a much less decrease than what we would expect. Eventually getting back to pure, which would be exactly what you would expect. So depending on what quantities this is in, it's either going to be more repulsive and make more volume or less repulsive. Not super huge amounts, mind you, but still noticeable changes. And the problem with the real solutions is there is no simple model. We can't just go, woo, it works, and then have the math work out so nicely. But we can use something called a limiting law, where it says a solution approaches infinite dilution, the real solvent will approach the ideal. And so we're going to do a lot of things where it's like really small dilutions and this limiting law. So use some calculus to help approximate these guys. But we can split these real solutions into two parts: a pure solution and a deviation from the pure solution due to Raoult's law. And saying that, so the mole fraction, the chemical potential of a solution is equal to the chemical potential of the pure solvent plus RT ln pressure over P pure. Now, because it is real, this is not simply Raoult's law. Raoult's law said that the partial pressure is equal to the mole fraction times P pure. But because this is not mole fraction, this is not ideal solution, this does not simply equal the mole fraction. So this would be something you actually measured, and that's known. So we'll look at this deviation from the ideal as an activity of the solvent. So the activity is like how it's deviating from the expected mole fraction right there. So activity is simply our P solvent actual divided by P solvent pure, but theoretical pure solvent, which can be measured. And of course, with activity, if you've had analytical, activity must also have an activity coefficient. For an ideal solution, the activity of a solvent equals the mole fraction of solvent. But this differs from a real solution by a deviation factor by gamma, which is our activity of solvent, such that activity of solvent divided by the mole fraction of the solvent. So this is the mole fraction activity, essentially mole fraction real over mole fraction ideal. That deviation is that activity coefficient. Much like our fugacity of a real gas, activity coefficient follows the same limit, that as pressure approaches 0, fugacity approached 1, so it becomes ideal. While as mole fraction approaches 0 for the solute, so as that mole fraction of solvent approaches 100 or 1, the activity coefficient approached 1. So we can use this to describe our real solution, saying that the chemical potential of a solution is the pure solvent chemical potential plus RT ln activity. So we know that as water is in excess, the solvent, it is close to the ideal modeled by Raoult's law, but ethanol is not, and that's suggested. So those are so we have, so this red curve is water. See that the little dash line underneath that is, the little dash lines underneath all of those are the ideal. So we're saying as water, the amount of water goes up, the pressure of water goes up, and it goes, when that's 0, it is dropped down to nothing. If the amount of ethanol is 0, it's 0, and then some. And this is how we'd expect it to be if we just use these from ideal. As water is in excess, you see a lot less deviation here. You do see some deviation. The pressure is going up, 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 and then starts dropping back down as it gets closer and closer to 0. Ethanol starts shooting up, and then it starts going back towards the line, modeled by Raoult's law, as it approaches 100%. And see this, the P total is the sum of these guys. So you get a lot of deviation overall. But you get to very little deviation in this region. But right now, we could almost draw 2 asymptotic lines for these guys. Right here, I'm going to notate this real quick, just to make sure you can see it. Actually, I'm going to make little lines. So there. So we have these two asymptotes. In the middle region, yeah, I want to say, where'd my mouse go? In this middle region, yeah, I'd say no, you probably cannot get a good probably can't get too good of a you can't get too good of a accuracy. But as we get dilute in one way or the other, we kind of get you can kind of get some accuracy on either end of the spectrum. So the asymptotes are kind of helpful. And that's going to play into what we're going to look at in a bit, which is Henry's law. So in dilute solutions, Raoult's law can model the solvent with some accuracy. But how do we model the solute? So we can model the solvent with Raoult's law. How do we model the solute? So in the opposite case, the solute is surrounded by a majority of solvent, so experiences a drastically different interactions. So we can't just use Raoult's law, but Henry's law can be used to model the solute in dilute solutions. That the pressure of a solute times the mole is equal to the mole fraction of solute times the Henry's law constant for that solute, depending on both solute and solvent to quantify the deviations. So Raoult's law only depended on the solvent because it was a kind of a colligative property that didn't really care about what was dissolved, and especially if you're considering that it's infinitely dilute, that the solvent mostly sees other solvent molecules. So it didn't really care about what was mixed into it. But the solute, if it's infinitely dilute, does care. So you have a Henry's law constant, which depends on both what the solute is, but also what it's dissolved in. So from here, we can get the ideal dilute solution is a solution where the solvent can be modeled by Raoult's law and the solute can be described by Henry's law. So we can get some degree of accuracy. Or this asymptotically, you're like, look, we have an asymptote right here where getting lower and lower. Now, and you may have noticed that the range of concentrations where ideal dilute solution exists is very small. So what do we actually do for the in-betweens? Activity and activity coefficients are used to measure the deviation between the ideal and the real data, but we cannot use them to just predict the expected results. It's more like we measure and then modify, but we can't calculate and predict. You can go, oh, okay, that's deviating by this much from what we expect, but we can't say the answer should be this if I read it on the meter. So, but for a given solvent solution with the solvent, the chemical potential of the solvent is the chemical potential pure of the solvent, RT, P solvent or P star, with that being the activity. And the activity coefficient being A over X, or A over the mole fraction. So the solute treated differently. So the chemical potential of the solute in solution is equal to the chemical potential pure solute plus RT ln mole fraction solute times Henry's law constant solute over P star of solute. So that becomes just the chemical potential Henry's of the solute. So that's a little different. Plus RT mole fraction solute. And this right here, the P star H, is just we encapsulate this, and that's a constant. So we're able to pull that in to a just part of a larger constant, where the core activity of the solute is pressure solute over K solute, and activity coefficient is activity of the solute over mole fractions. So, calculate the activity and activity coefficient of both carbon disulfide and acetone if the mole fraction of carbon disulfide is 0.9191 and the mixture and the carbon disulfide and acetone mixture if respective pressures is 490.7 and 123.4 torr. So then it gives you some P stars and whatnot. So let's start by like writing down our Raoult's law and our Henry's law. Raoult's law said that P equals X P star. And Henry's law stated that P equals X KH. Now I'm going to jump back one slide real quick. Just to look at there. So activity per mole fraction. Here we go. Okay. Activity of the on this case is A. Activity is P over P star, and activity coefficient is mole fraction. And this guy is about like P over K. Okay. A P over A over X. Okay. So we got all of our equations. We got our mole fraction. We got our IV, the pure pressures. We got our we got our mole fraction. We got our pure pressures, and we got our Henry's constants. We're not going to need all these to do all this. We will need just part of these. But let's start by what is the mole? If the mole fraction of CS2 is 0.9191, then the mole fraction of acetone, we're going to need that guy no matter what. Acetone is going to be 0.09 0809. Let's go. 0809, because adding up the two mole fractions should give us 1. So mole fraction 1 plus mole fraction 2 is 1. Now the respective pressures. So let's start with CS2. CS2, the activity of this is 490.7 divided by 512.3. So 490.7 divided by 512.3 is going to be an activity of 0.9578, and the activity coefficient would be that number divided by our mole fraction. So 0.9578 divided by 0.9191. So we have activity coefficient this is essentially 104% more active pressure than we would expect. The pressure's jumped up by a little bit. 1.04, maybe we'll say 2. Now the activity of our acetone, which is in a lower quantity, is going to be what? 123.4 divided by 1950. Okay, that's going to give us 0.06328, and then our activity coefficient is going to be then that number divided by our mole fraction, 328 by 0.0809. So that's going to have it's going to be 78% of what is expected. So it's actually going to be a much lower effect. So we don't need the Henry's law constant for carbon disulfide, but carbon disulfide is clearly going to be the solvent. We don't need the P star of acetone because acetone is clearly the solute. If I had used those numbers to try to predict the mole fraction would have been of acetone should be like 0.35 to get that pressure, but it's actually 0.0809. Now, there's some further applications of these activity coefficients. Much the same way we converted X to the mole fraction to molality and molarity and colligative properties, we can convert the activity coefficients to fit the molality and molarity. So we add it to the freezing point depression, the activity coefficient to molal, boiling point elevation, and the osmotic pressure. They cannot predict real data. It can be used to measure deviation from what is the ideal, once again. And of course, Henry's law can be used to calculate the solubility of gases. This is where you've probably seen this, if you've seen this at all. That the mole fraction, the chemical potential of a solute in solution is equal to but this is all constant. The chemical potential of the pure solute is RT ln activity. Now, because of the nature of this, it does not matter if we're discussing a pure solid, a pure liquid, or pure gas. So in most cases, in the case of pure gas, it fits with the chemical equation that A aqueous interchanges with A gas. So most gases are sparingly soluble in water, making Henry's law appropriate. Because remember, Henry's law needs a dilute solution. So we could say that, well, mole fraction of the gas, which is the same as our activity, is moles of A over moles of A plus moles of water. Where if the amount of water is much, much greater, then this simply simplifies to moles of A over moles of water. So really a molar solubility. Such that we can say that if moles of A is equal to moles of water times mole fraction A, the reaction further simplifies to the solubility is the moles of water times pressure of water over the solubility constant. Meaning the amount of gas soluble in water is directly proportional to 1, the amount of water, 2, the Henry's constant, and 3, the pressure of the gas. So we can figure out exactly how many moles of A we have in water based on how much water you have and what pressure you have and this constant. Now, the last thing we'll talk about just briefly, we won't really want to use because I hate using this, is that recall with Gibbs of a reaction, we said that, okay, it's a sum of the moles times the chemical potential. Essentially, that's the coefficients times the chemical potential. And that would equal 0 at equilibrium. And then at equilibrium, Gibbs standard is equal to RT ln K. So in order to express K of reaction in a dilute real solution, we would have to use Henry's law constant, where chemical potential is that constant again, chemical potential pure, Henry's RT ln X. So that becomes, all this is a constant, plus RT sum of ln activity raised to the power of the coefficients, such that essentially what happens is the concentrations that we would have used to K now become activities. And the activities here, so we're going to use K as, this is a new concept. Instead of a sum, this is a product. We just say the product of activities, but this is something we've seen before. There's product over reactants multiplied together raised to the power of the coefficients. So all this is saying we're multiplying this whole mess by the activity as well. But for most dilute non-electrolytic solutions, we're going to just simply approximate this. It's ugly. No one wants to deal with it, so we're not going to worry too much. K is usually this, and we could just ignore it. We ignore all the activity and activity coefficients. But if we went to actually look at where it deviates, we would have to deal with that. We're not going to. Too much of a mess. I hate the whole aspect of just looking at deviations rather than looking at data you can predict. So I'm not a big fan of activity. But that is the end of this chapter. And now after this chapter, we'll start looking at some more solutions and like maybe electrolytic solutions, and it keeps getting messier. We'll try to do it as best we can, so keep on keeping on. If you like this video, please like, please subscribe for more videos. I got a few more chapters to get through, so see you when I see you.